All right, physics reaction video number 60. That's a big milestone, so that's exciting. You go 2 whole months watching these, I guess. Today, I took me a while to find a search that worked. I ultimately did 12th grade physics, filtered for the last week. This is what I found. So I assume this must have 12th grade in it somewhere, but I'm not actually sure. And so we're going to learn about electric charges and electric fields. Exciting. Here we go.
Welcome back. Today we're going to talk about electric charges and electric fields. And both of these words, electric, come from the word electron. Electron, as you probably already know, is a particle that is charged negatively and it moves around the nucleus of an atom. All atoms have electrons around them. So
Nice.
Because every material is made of atoms, every single object in the world has electrons. But some of them have the possibility of electrons moving easily through them, and some are harder for electrons to move through. So these are divided into 2 categories: electric insulators and electric conductors.
So there's a little bit of post-editing. You can see that there's some pauses, and there's the dumb focus problem. God, I hate those cameras. But it looks like the bulk of the image is the whiteboard, so I'm sure it'll stay in focus almost all the time. The post-processing is so interesting, right? Because it takes a little bit of effort to go back. It means that she very likely watched herself and decided, oh boy, no, that would lead the students astray. I'm going to just cut that. Or, oh man, that was inefficient or whatever, and I'm going to cut that. And so it's so interesting. It kind of depends on the relationship that you have with your students, right? Because if you know that you're going to have an opportunity to talk with your students and say, hey, I know I said that, but really I meant this. That's one thing. If you're a little bit worried this is going to be a standalone video that anyone might see years from now, then yeah, post-processing makes some sense. So let's watch and see. I assume she'll get to some, I don't know, calculations or something. Let's watch for more cuts and see, if the flow gets affected. I mean, so far so good, right? What I really liked about the way she started was talking about sort of where the stuff comes from in the first place. It's one thing to say, let's pretend we have a charged particle and let's go do Coulomb's law, right? And it's another to say, well, where do these charges come from in the first place? So she's already talking about conductors and insulators, and I think that's really, really interesting because static electricity is something that we have experience with, but what's actually happening with static electricity is a really interesting question. And so I think that really sort of laying out where the stuff comes from is useful.
Conductors. So electric conductors are materials through which electrons can travel easily. An example of one of these.
So there was a great example of a cut, right? So she cut from about writing the letter M all the way to the end of the sentence. And so that, very, very likely, if she's anything like me, if she's sitting there writing, it's hard to talk and write at the same time, right? And so do we really need to capture, writing all that down? And if you compare that to doing it in person, if you really want the students to get something in their notebook, one way to ensure it is to leave them enough time to do it, right? And so it takes them about the same amount of time as it takes you to write. And so from that perspective, in person, it's okay that you might spend 3, 4, 5 seconds writing without talking at all. Of course, you're in the way and the students might not be able to see it. But for this video, right, to say, okay, look, I'm just trying to teach you some things here. There's no reason to show the entire sentence being written. So I'm curious what you guys think, right? Because there's the logistics of, I have to go do all of the post-processing. There's the time for the students to think. There's the clarity of the presentation. There's the fact that, let's be honest, that we notice the cuts, right? They're not hidden. I'd love to hear more about that.
These materials is metals. Metals can be charged because electrons can travel easily through them. So metals. And then we have electric insulators. So insulators are materials in which electrons can't travel easily. It's hard for them to move around.
Let's see if there's a cut this time.
Some examples would be plastic and rubber. So when you have an electric conductor, so electrons can move easily through it, you can do something that is induce a charge into it. So all objects are naturally neutral in charge. They don't have a net positive nor negative charge. But if you put close to it something that has a charge, you can induce a charge in a neutral object. So this is called induction of charge. And it looks something.
So I'm really curious to see how she wraps this together. So I would ordinarily think that this stuff she's talking about now would be not on the same day as electric fields, right? So how long is this video? 13 minutes. Hang on, I gotta sneeze. Oh, it's going away. 13 minutes long. So I'm curious to see how she gets to electric fields from here, because for me, in the typical way I would present this, this would be this stuff that she's talking about here would be a different day. So not because they aren't connected. Of course they're connected. And in fact, to really explain how this induction of charge works, one of the easiest ways to do that is to talk about how the field works. So, and if I think about like the difference between teaching at the college level, like an intro course where we might hit this, and like an advanced electromagnetism course. Well, in the advanced electromagnetism course, we come back to this stuff, but we explain almost everything from the perspective of field. I mean, we just jump right to the field to explain, oh, well, this is why these charges move here, and this is what's going on, or potential for that matter. So, I guess I was making an assumption about who her target audience is. It feels more like the intro physics than the advanced stuff. So I'm really curious to see this, because I'm excited that maybe this is a better way to go about doing this.
Like this, imagine you have a positively charged object. That means that it has positive charges all over, more positive than negative. And you put it close to, let's say, a very small piece of paper that has positive and negative charges, because it's made of atoms, and atoms have protons, which are positive, and electrons, which are negative. So let's say it's neutral in general. But when you put this close, when you bring it close to a piece of paper, what's going to happen is that the charges are going to move. So you have a piece of paper. And what you need to know about charges is that like charges, the same charge repels the same charge, and opposite charges attract. So don't forget that. Like charges repel, and opposite charges attract.
I mean, there's an interesting example where a cut could have happened, but it was short enough. Oh, and she did put a little cut there.
Negative and positive attract, positive and negative attract, but negative and negative repel, and positive repel.
Cool.
So if you put a lot of positive charges
the autofocus.
to the paper, the negative charges in it will feel an attraction, because positive attracts negative. So the negative charges will all move to the left to be close to the positive charges, while the positive charges will feel the repulsion from the other positive charges, and they will move to the other side. Right? So this means that a charge was induced in the piece of paper, because it was neutral, but now it's sort of charged, because now this part is charged positive and the other part is charged negative. So that's induction of charge. But this induction of charge is temporary. As soon as you take away this positive charge, the charges will realign, and again, it will be neutral. It won't be charged anymore. And something else to remember is that the charges will be conserved. I'm not sure if I drew it correctly, but the same number of charges that
was awesome.
At the beginning will be there at the end, because of a very important law called conservation of charge. What conservation of charge basically means is that no matter if the charge is rearranged, you will always have the same total amount of charge that you did before. So we can use this conservation of charge to do an example. So suppose you have two charged metal objects, so they are conductors. One has a charge of +2, and
You know, it's interesting. So she had originally described, I think she said this was metal and this was a sheet of paper. And so when the paper experiences this induced charge, right, the separations are actually pretty small, because it's an insulator. Paper is an insulator, right? And so this kind of charge separation happens, but it's actually on a pretty small scale. but it's usually enough because of Coulomb's law, right? The distance for the paper to be attracted. That's why little bits of paper are attracted to charged things, whether this is positive or negative. So now she's shifting to what she said was two metal things. And of course, then you really can get this macroscopic separation of charge as she drew it here. Really, everything she set up here would have worked no matter what this was. It's just a matter of like how far apart, like basically how far they can move. But now down here, she's talking about some metal, so we should see or can expect some macroscopic changes.
Let's say the other one has a charge of -1, right? And you put them together. Because they are both conductors, the charges can actually jump from one ball to the other.
Yeah.
So they will move and rearrange between the two objects. So what happens is that here there was a total charge of 2 - 1, +1. So here there's also going to be a charge of +1. But when you put them apart,
you know, it's interesting. My brain right away went to like exactly how would they distribute, right? Like the total charge makes sense, but now that, yeah, you know, we're going to get some positive over here and some positive over here. They're going to run away from each other, but by how much, right? Like it's bigger, so it should probably get more. And it turns out that's super complicated, right? So the exact distribution of charge to calculate is hard, but certainly the stuff that she's hitting here is really, really interesting. It feels like, oh, I've got, you know, opposites attract, and then they attract, and then they run away. And there's this really, really great demo that we do with pie plates and charged pith balls, right, where it goes rattle, 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 rattle. It's basically transferring the charge back and forth. That's actually a really cool demo. It's loud if you ever try it. But the shape makes things really hard to calculate.
because these charges will mix, then the charge will divide equally between the two objects. So
I'm not sure.
Then we will have, you know, here there's just going to be who knows where, +2 and -1 between the two. But when you separate them, what you're going to have is that they divided equally. So in order to give plus...
Let me think about that. Definitely when they're together, when they're touching each other, they definitely have some really crazy distribution of charge. I mean, shape, it's just a funny single shape now, right? And definitely it doesn't have any symmetry, so exactly where the charges are is hard to calculate. But I think more charges on the big one than the small one. But then right upon separation, I'm not sure. It looks like she's about to say that it's half a unit of charge in both, but I'm not sure that's true. Certainly they're both positively charged. And that's actually the big point here, right? That you went from things that used to attract each other to now they're going to repel each other. But I'm not sure it's half and half. What do you guys think about that? I've not done the experiment. How do you measure the charge? Oh, you can do it. The shape, the size has me pondering that.
1, to have them divided equally, this has to be +0.5, and this has to be +0.5. So even though there is no longer a negatively charged object and a positively charged object, but two positively charged objects, they do follow the law of conservation of charge, because the total charge at the beginning was +1, and the total charge at the end is +1. So for this, you need to remember two things: that the total charge always has to add up to the same thing, and that if you put together and then draw apart two objects, the charge will divide half and half. Now let's talk about...
So it's interesting. So, I mean, I'm not sure, right? I'm not sure about the very last thing that she said, but certainly the idea that they're going to share and then come apart, and both whatever the sign of the shared is, you can absolutely know that they're both going to go apart with that same sign. Whether it's evenly split when they're not the same size, I guess I'm thinking about this analogy, the temperature analogy, right? You get a hot thing and a cold thing, a big one and a small one, and you put them together. Well, they reach some common temperature. Then you pull them apart. Well, now they have the same temperature. So from a temperature analogy, absolutely yes. But I think the right analogy here is, I guess, units of energy, right? Like, this is really hot, this is hot, this is cold. This has a lot more units of thermal energy than this one does. They get together, they share their units of energy, but they share them such that the average energy per mode, right, of existing, that's the statistical dynamical definition of temperature, is the same. So you pull them apart, they have the same temperature, but this still has way more energy, like total energy. So that's the analogy I'm going for. So help me. I'm not sure, but interestingly, it doesn't actually impact really the big point she's saying. This idea of the sharing, the idea that they can go from attracting each other to repelling each other, I think is the really, really big idea.
Electric fields. So any charge, either positive or negative, has around it an electric field. An electric field means an area around a charge where other charges will feel a force. So let's say you have a positive charge in space.
Yep, I love
nothing else, just a positive charge.
Grounding it in force.
If you put another positive charge, let's say here, because equal charges repel, this charge is going to feel a force that pushes it away from it. So
for me, what the electric field does is it allows you to sort of explain what's happening locally. All the charge needs to do is look around itself and say, what is the field right here? Oh my God, it's telling me to go that way. Okay, I'll go that way. So compare that with, okay, let me find out where all my friends are. I'm like, oh, okay, there's a positive charge over there. Oh, I need to run away, right? Like the idea that you don't actually need to know what created the field. You just need to access locally, right here, what field am I feeling? So this notion of opposites attract and like charges repel helps you when you can draw the whole picture. But if you ask the question, why did this move? That's where I think the field is useful.
That charge here will feel this force that pushes it away. And the charge here will also feel force pushing it away. So this is how we represent an electric field for a positive charge.
Cool. And I love how the density of arrows can indicate strength.
Of the direction in which a positive charge would move if it were placed there. So placed here, it would move in this direction. If a charge were placed here, it would move in that direction, away from the positive charge.
Cool.
If we have a negative charge, it's going to be the opposite. So if we have a negative charge and we place a positive charge, because positive and negative attract, this positive charge will feel a force towards the negative charge.
Awesome.
A positive charge over here would feel a force towards this negative charge. So how we represent an electric field for a negative charge is with arrows going towards it.
Cool.
The opposite to a positive charge. So for example, if you have this charge, you place it here, and it moves away from the charge. It's this natural movement, and it will accelerate the charge, so it'll give it some kinetic energy, some energy of motion. So a charge moving naturally by the electric field it feels will gain kinetic energy, and it has to do no work. So charge moving naturally gains kinetic energy and does no work. But what if instead we wanted to do the opposite? What if we wanted to move this positive charge closer to the positive charge? Or what if, even though there's an attraction here, we wanted to move this positive charge away from a negative charge? Then we would have to do work. So to move a charge away from the natural...
So it's interesting, right? I think that there are some people who would say this is negative work. Basically, it gains this kinetic energy by cashing in potential energy, or that this thing is doing work to speed it up, right? But I use very similar phrases, right? Like that we didn't have to do anything. It'll just naturally, I love this word here, it'll just naturally go away. And then what she's talking about now is to make this charge go away, or to make this charge go in, an external object needs to do some work. So I find that really, really useful when helping students understand all of the signs of everything, right? Like the potential and the potential energy. Like, well, did you have to do some work? That's what I'll say. It's like, did you have to work to get it there, or did it just want to go there naturally? And that helps with the sign. But, I think that it's tough when people talk about negative work. They don't like it. I think that this is a little bit easier to understand, right? That it's, nobody had to do anything, right? Some people say, well, no, this charge is doing the work. I mean, anytime you have a kinetic energy change, somebody has to do work. Yeah, but she's talking about, like, you, right? So I think that's really, really interesting. Well, given the time, I think I'll pause here. Some really, really great stuff in here. She did actually get us to electric fields pretty fast. That was super interesting. I thought that the idea of bringing things together and pulling them apart, the charge by induction, all of that stuff was really, really cool too. All right, everybody, have a great day. And remember, physics teachers are awesome.